Hi everyone, today we're going to talk about the galvanic cell. This is tied to the learning objective from College Board. First, the student is able to identify redox reactions, and we can make qualitative and quantitative predictions about galvanic or electrolytic reactions based on half-cell reactions and potentials and the Faraday's laws. And students can analyze data regarding galvanic or electrolytic cell to identify properties of underlying redox reactions. Electrochemistry is the study of redox reactions that occur within electrochemical cells. In a galvanic cell, electrical current is generated spontaneously. However, in electrolytic cells, electrical current is driven by an externally applied electrical potential. And here in this video, we're going to look at galvanic cells. First of all, we need to review balancing oxidation-reduction reactions. The procedure is one, to separate the overall reaction into two half reactions and identify which is oxidation, which is reduction. Now then we balance each half reaction by mass. And this is done by balancing all elements. And after we balance the elements, we then balance the oxygen by adding water. And that would create additional hydrogen. Therefore, we now balance the H by adding H plus, the positive ion. And if we are going to do this in basic solution, we need to neutralize the hydrogen ion by adding appropriate number of hydroxide ions to neutralize it. Then we balance the charges by adding electrons where appropriate. And we multiply either one or both half reactions by a small whole number to make the number of electrons equal. Finally, we add up the two half reactions and cancel out the electrons. Now let's try this one here. Balance in acidic medium, copper and nitrate ion to form copper 2+ ion and NO2 gas. First of all, we would write the half reaction recognizing copper is oxidized into copper 2+, and to cancel out the charge of 2+, we add 2 moles of electron to the product side. Then the second reaction, the half reaction, is the nitrate ion being reduced into NO2. Now looking at the oxygen atoms, we have 1 mole on the left. Therefore, we add 1 mole of water to the right on the product side to balance the oxygen atoms. In doing so, we created 2 H atoms on the right, so we now add 2 moles of H plus to the left to balance it. Finally, looking at the charges, we would have +2 and -1 on the left-hand side, which is +1 net charge. Therefore, we cancel that out with a -1 electron on the left-hand side. Now then we take that reaction and multiply that by a coefficient of 2 because we want to make the electrons equal in the two half reactions. And then we add it up. We finally have copper metal and 4 moles of H plus hydrogen ion and 2 nitrate ion in aqueous solution to form Cu2+ and 2 moles of NO2 gas and 2 water. And if you look at both sides, the number of atoms should be balanced, conserved, and the charges should be the same. Now let's try another equation in which we balance it in a basic medium. We have chromium 3 hydroxide solid and the hypochlorite ion to form the chromate 2- ion and chlorine gas. So first in oxidation, half reaction, we start out with the chromium 3 hydroxide, which is oxidized into chromate, the chromate ion 2-. Now looking at the oxygen atoms, we have 3 on the left and 4 on the right. Therefore, we add 1 mole of water to the left, and that creates a total of 5 moles of hydrogen atoms. So we add 5 moles of hydrogen ion to the right, and to balance the charge, we add 3 moles of electrons. For the reduction half reaction, the hypochlorite ion is reduced into chlorine. First of all, we multiply the hypochlorite by a coefficient of 2 in order to balance the number of chlorine atoms. Now then we add 2 moles of water to the right-hand side in order to balance the O atoms. That would create 4H, and therefore we add 4H plus to the left. And finally, balance the charge with 2 moles of electron to the left. And because we want to equalize the number of electrons in the two half reactions, therefore we multiply the oxidation half reaction by 2 and the reduction half reaction by 3. Now you can add it up, and the following equation is obtained. However, we want it to happen in the basic medium. That means we need to neutralize the hydrogen ion in the reactant side. To that, we add 2 moles of hydroxide ion. Now we add the 2 moles of hydroxide ion to both sides, to the left as well as to the right. On the reactant side, the left-hand side, the 2 moles of hydroxide ion neutralized by the 2 moles of H plus will form 2 moles of water. And that 2 moles of water can be reduced by the right-hand side 4 moles of water. And therefore, now you would have 2 moles of chromium 3 hydroxide and 6 moles of hypochlorite ion to yield 2 moles of chromium ion and 3 moles of chlorine and 2 moles of water plus the 2 moles of hydroxide ion. Now here is a problem relating to galvanic cell and the setup. In the reaction, we have zinc metal reacts with copper 2 plus ion, forming zinc 2 plus ion and the copper metal. Now here's a diagram showing the setup. And in the left-hand side, where you have the zinc electrode put into 1 molar of zinc nitrate solution, and in the right side compartment, we have copper electrode put into the copper nitrate solution being 1 molar. Now, the oxidation happens at the anode. This is something we should remember. So at the anode, you have zinc metal oxidized into zinc ion, releasing 2 moles of electrons. The reduction always happens at the cathode. So we have copper 2 plus ion gaining 2 moles of electron to be reduced into copper metal. The electron will flow through an external circuit from the anode to the cathode spontaneously, as indicated by the red arrow, and the voltmeter will register a voltage of 1.10 volts. In that sense, because the zinc metal is being oxidized, the zinc electrode will lose mass later. And in a sense, the copper ion is reduced to be deposited as copper metal on the copper electrode. Therefore, the copper electrode will gain mass. If we examine the zinc ion concentration in the left compartment, it will increase as more zinc ions are being made. And the copper ion in the right cell will then decrease because it's now being reduced into copper metal. However, this flow of electron will stop soon after because there's a buildup of too many positive zinc ion in the left cell, and there will be too many nitrate -1 ion in the right cell, and that will stop the electron flow. The way to solve the problem is to insert a salt bridge, which is like a U-tube glass tubing, and inside we put some cotton balls that's been wet with sodium nitrate. Now, because sodium nitrate is ionic, the nitrate ion in the salt bridge will then be attracted to the zinc ion in the anode compartment to neutralize the buildup of positive charges, while the sodium ion, the cation, will be attracted into the cathode compartment to neutralize the buildup of nitrate ions, and then the electron flow will resume. And this is an important function of the use of salt bridge in a galvanic cell. When we talk about cell potential, we are referring to electromotive force. Now, electrical current is measured in the units of ampere, A. And 1 ampere is equal to 1 coulomb per second, meaning the flow of 1 coulomb of electrical charge per second in time. Current is driven by the difference in potential energy in the unit of voltage. So 1 volt is equal to 1 joule per coulomb, meaning the difference in potential energy in joules per unit of charge. The cell potential is a difference between two electrodes, which is represented by E naught of the cell. The little circle I call naught, meaning standing for standard cell potential at standard conditions. And the standard conditions is 1 molar for aqueous solution, 1 atmospheric pressure for gas at room temperature, 25 degrees C. For spontaneous reaction, the cell potential has to be positive. This is something we need to remember. Now, because the cell potential can only be measured when two half cells are combined, therefore we must find something that we call standard. And in this case, we employ the hydrogen electrode, and which is abbreviated as SHEC. So in the hydrogen electrode, the zero cell potential is arbitrarily assigned for the reduction of hydrogen ion into hydrogen gas. Now, as depicted by this diagram, so there's an inert platinum electrode immersed in 1 molar of hydrochloric acid with hydrogen gas at 1 atmospheric pressure bubbling through the solution. So once we have the standard hydrogen electrode with the 0 voltage potential, other electrode potentials are then measured relative to this SHE. If you look at your book, in the appendix section, you'll find a table of reduction standard potentials. Remember, they are always given as reduction at 298 K. Now you will notice that there will be some more positive cell potential, meaning that they have a stronger tendency to be reduced. They are the stronger oxidizing agents. And as you follow through the table, you'll find that it's becoming more negative now in the cell potential, and it means they have stronger tendency to be oxidized, and they are weaker oxidizing agent. When we calculate the cell potential, the electrode with more negative cell potential tends to lose electrons to undergo oxidation. And the electrode with the more positive cell potential tends to gain electron and undergo reduction. So when we calculate the overall cell potential, it is equal to the cell potential of the cathode minus the cell potential at the anode, or I like to use this equation a lot myself, is equal to the reduction potential at the half cell plus the oxidation potential at the other half cell. And the overall cell potential has to be positive for the reaction to be spontaneous. So if we calculate and get a negative cell potential, that means the reaction is non-spontaneous. Now consider two reduction half reactions. One is the reduction of lead ion into lead. The cell potential is negative 0.13 volt. And the reduction of chromium 3 plus ion into chromium. The reduction potential is negative 0.73 volts. Because the chromium half reaction has a more negative cell potential, it repels electrons, and it will go in the reverse direction, which we then flip the equation over to become oxidation. Now the lead half cell has less negative cell potential. It will attract the electrons and go in the forward direction, what we call the reduction. So now as we flipped the chromium reaction, the half reaction, and it becomes oxidation, and we change the sign from negative into positive, because as we used to have reduction potential, now we make it into oxidation, we change the sign. And then we look at the reduction of the lead ion. Now because the electrons are not the same, we multiply the oxidation by 2 and the reduction by 3. And we leave the reduction potential of lead ion as if. Now, as we add up the two half reactions, we have 2 moles of chromium metal and 3 moles of lead 2 plus ion to form 2 moles of chromium 3 plus ion and 3 moles of lead, and the electrons would have been canceled out. The overall cell potential is the oxidation cell potential plus the reduction cell potential, which is 0.73 minus 0.13, which is positive 0.60 volts. And therefore, the reaction is spontaneous in the forward direction with a positive cell potential. Practice problem number 1. Given the reduction of aluminum ion with the cell potential of 1.66 volts and the overall reaction with an overall cell potential of 2.62 volts. Find the reduction potential for the nitrate to become NO gas. Now, because if we look at the overall reaction, the aluminum is oxidized. Therefore, we need to turn the given reduction of aluminum ion into oxidation of aluminum metal. When we flip the equation, the cell potential now becomes oxidation, and the sign is changed to negative 1.66 volts. Now, this overall cell potential is equal to the oxidation potential and the reduction potential. Given the overall cell potential is 2.62 volts, and the oxidation potential is negative 1.66 volts, now we can calculate the cell reduction for the half reaction is 4.28 volts. Another thing we need to learn is how to represent the cell setup in terms of cell notation. Now, here we have the oxidation on the left-hand side, meaning it's happening at the anode when zinc is oxidized in zinc 2 plus ion, and the reduction is written or notated on the right-hand side, representing the reduction at the cathode. Notice there's a single vertical line separating zinc metal from zinc ion. That's for phase separation, a boundary for phase separation. And if the substances are in the same phase, we separate them by a comma. The double line in the middle representing the salt bridge. Try this problem. Write the electrochemical cell notation for the iron and permanganate to form iron 2 plus and manganese 2 plus ion in acidic medium. As we note, the iron is oxidized into iron 2 plus, giving out 2 moles of electron. And the permanganate ion is reduced into Mn2 plus and gaining 5 moles of electron in 8 moles of hydrogen ion. To equalize the number of electrons, we multiply oxidation half reaction by 5 and reduction half reaction by 2. Now when we write the overall cell notation, we start out with the left-hand side, the anode compartment. We start out with the iron metal separated from the iron 2 plus ion with 1 single bar. And then in the middle, we insert the double bar to represent salt bridge. And then we go on to the cathode side where we have permanganate ion, hydrogen ion, and Mn2 plus ion all in the same phase. So we separate them by commas. Then for the phase boundary, we insert a single bar to represent separation of the aqueous solution from the platinum electrode, which is solid. So the whole overall is going from anode to cathode in the notation. To summarize what we have learned today, we learned how to balance redox reactions by half reaction method in an acidic and a basic medium. We learned how a galvanic cell operates. We also learned that standard cell potential is measured relative to the standard hydrogen electrode set at 0 potential. We learned how to calculate the overall cell potential for galvanic reactions based on half reactions and potentials. And we learned how to predict the spontaneity of a redox reaction in a particular direction. Finally, we learned how to use notations to represent electrochemical cells. I hope that you have found the video helpful. If you like it, please give us a like, and I look forward to seeing you in the next part of this video.